Hello students, welcome to this lecture on complex numbers and quadratic equations theory. In this lecture, we will cover NCERT section 4.3.5, 4.3.6 and 4.3.7 and examples 2 to 4. So let's start. This is disclaimer. So we will first look at power of iota. Remember, I is defined as the square root of iota. Behaves when raised to different powers, is essential for working with complex numbers. So we will know about power of iota. Then we will talk about the square roots of a negative real number. Next, we will look at some important identities involving complex numbers. Finally, we will solve examples 2, 3 and 4. I hope you are ready with your notebooks and pens. So let's get started. So look at first topic of this lecture, that is power of iota. So we are now going to explore the cyclic nature of power of iota, where iota is the imaginary unit defined as the square root of -1. So we will look at how the powers of iota repeat in a periodically. Okay. So let's begin by calculating the first power of iota. We have iota to the power 1 is iota. So this just means that raising I to the power 1 gives us I itself. Next, let's look at the second power of iota, that is iota square equal to -1. Then we will find iota to the power 3. Okay, so we have iota to the power 3 equals to iota to 2 square, iota square times iota, which is equals minus iota, since iota square is equal to -1. Then we will calculate iota to the power 4. So iota to the power 4 can be rewritten as iota square whole square. Since iota square is -1, so iota to the power 4 equals -1 whole square. This is simply equals 1. Next, let's see what happens with the fifth power of iota. So iota to the power 5 can be written as iota to the power 4 times iota. Since iota to the power 4 is 1, so 1 times iota is iota. So iota to the power 5 is equal to iota. So after 4 steps, the pattern repeats and we are back to iota. So this confirms that the power of iota cycle every 4 steps. Therefore, we can conclude that the power of iota, where I equals the square root of -1, repeat in a cycle of 4. This means that every time you increase the exponent by 4, you return to the same value as before. So this cycle property is very useful for simplifying higher powers of iota. So in general, for any k, we can summarize the pattern. First, iota to the power 4k equals 1. That is, iota to the power 4k is 1. Next, iota to the power 4k plus 1 equals iota. So, iota to the power 4k plus 1, it can be written as iota to the power 4k times iota, and this is simply equals iota. Then, iota to the power 4k plus 2 equals minus 1. So, if the exponent leaves a remainder of 2 when divided by 4, the result is minus 1. Finally, iota to the power 4k plus 3 equals minus iota. Since iota to the power 4k is 1, okay, and iota cube is minus iota. So, iota to the power 4k plus 3 is simply equals to minus iota. So, this completes the cycle. So, to summarize, the powers of iota repeat every 4 steps. Iota minus 1 minus iota and minus and 1, okay, and then the cycle starts again. So this pattern helps us quickly evaluate any power of iota. Now let's look at some useful identities involving complex numbers, specifically powers of the imaginary unit of iota. These identities will help us simplify the expression and solve equations involving complex numbers. So now we will go through each one step by step to see how they are derived and what they mean. So first, let's examine I raised to the power of negative 1. So the equation is I to the power minus 1 equals 1 divided by iota equals iota divided by iota square equals iota divided by minus 1 equals to minus iota. Using here iota square is equal to minus 1. Next, let's look at I raised to the power of negative 2. The equation is iota to the power minus 2 equals 1 divided by iota square equals to 1 divided by minus 1 equals to minus 1. Using here iota square equals to minus 1. Now let's consider I raised to the power of negative 3. So the equation is I raised to the power of minus 3 is equal to 1 divided by iota cube is equal to 1 divided by minus iota is equal to iota divided by minus iota square is equal to iota. Using here iota square is minus 1 and iota cube is minus iota. Finally, let's look at I raised to the power of negative 4. So the equation is iota to the power minus 4 equals 1 divided by iota to the power 4 equals 1 divided by 1 equals 1. Using here iota to the power 4 equals 1. Let's look at an example involving powers of the imaginary unit iota. So the question asks us to evaluate I raised to the power 39th power. So first of all, try it yourself and then see solution. So now let's move on to the solution. So we will break down the steps together so you can see exactly how to approach problems like this. First, let's restate what we are given. So we need to find the value of iota to the power 39. So remember, iota is the imaginary unit in complex numbers defined as the square root of minus 1. To solve this, we start by dividing the exponent by 4. This is because the powers of iota repeat every 4 steps. So let's see how many times 4 goes into 39. When we divide 39 by 4, we get 39 equals 4 times 9 plus 3. That means 4 goes into 39 times 9 times with a remainder 3. This remainder tells us where we are in the cycle of iota's powers. Now let's apply the general formula. Iota to the power 4k equals 1. Iota raised to the power 4k plus 1 is iota. Iota raised to the power 4k plus 2 equals minus 1. And iota raised to the power 4k plus 3 equals minus iota. So we get iota to the power 39 equals iota to the power 4 times 9 plus 3 equals iota to the power 4 times 9 times iota cube equals minus iota. Since iota to the power 4 is 1 and iota cube is minus iota. Therefore, the final answer is iota raised to the power 39 equals minus iota. So this is our final answer, and I hope this example is clear to all of you. So this is a fundamental concept in understanding complex numbers and quadratic equations. So let's pay close attention to how we handle square roots when negative numbers are involved. So let's look at the definition. If a is a positive real number, then the square root of negative a is what we are interested in. So this sets up the idea that we can extend our understanding of square roots beyond just positive numbers. So square root of minus a equals square root of a times minus 1 equals square root of a times square root of minus 1. Since iota is equal to square root of minus 1, so this is equal to iota times square root of a. So square root of negative a equals iota times square root of a. Let's see this in action with an example. So we will find the square root of minus 9 and 7. So let's look at the solution. First, square root of minus 9 equals square root of 9 times minus 1 equals square root of 9 times square root of minus 1. Using here iota equals square root of minus 1, and this will give us square root of minus 9 equals 3 times iota. Next, square root of minus 7 equals square root of 7 times minus 1 equals square root of 7 times square root of minus 1, and this is equal to square root of 7 times iota. Using here iota equals square root of minus 1. Now let's address a common misconception. Many students think that the rule square root of a times square root of b equals square root of ab always works, but that's not true when both a and b are negative. It's important to know when this identity is valid. So the identity square root of a times square root of b equals square root of a times b is valid only if at least one of a and b, a or b, is non-negative. It is not valid if both a and b are negative. Okay, so students, you should keep in your mind this concept. So what's the correct method when both numbers are negative? So let's see how to multiply 2 square roots of negative numbers properly. So we start with square root of minus a times square root of minus b equals iota times square root of a times iota times square root of b. Using here square root of minus of a equals iota times square root of a, and square root of minus b equals iota times square root of b. Let's multiply. So iota times square root of a times iota times square root of b, this is equal to iota square times square root of a times square root of b. Since iota square equals minus 1, then we get this is equal to minus square root of ab. So square root of a times square root of minus b equals minus square root of ab. This is the correct result when multiplying square roots of two negative numbers. So remember, the negative sign comes from iota squared being minus 1. Okay, so this wraps up our discussion on this important property. Let's look at an example involving this concept. So the question is, find the value of square root of minus 2 times square root of minus 3. So let's start with the solution. So we will solve this problem step by step so you can understand easily. So first, let's define our terms. So given that z1 equals square root of minus 2 and z2 equals square root of minus 3. So here z1 and z2 represent two separate complex numbers and each involving the square root of a negative number. So now let's write the multiplication explicitly. So z1 times z2 equals square root of minus 2 times square root of minus 3. Next, let's express each square root in terms of iota, the imaginary unit. So remember, square root of minus a equals iota times square root of a, and okay, so using this formula, and we can write square root of minus 2 as iota times square root of 2 and square root of minus 3 as iota times square root of 3. Now let's simplify and multiply the terms, then we get iota square times square root of 6. Since iota square is minus 1, so z1 times z2 equals to minus root 6. Okay, therefore z1 times z2 equals minus square root of 6. So this result shows that multiplying these two complex numbers gives us a real negative value, not an imaginary one. And it's important to note a common mistake. Incorrect method, square root of minus 2 times square root of minus 3 does not equals to square root of minus 2 times square root of minus 2 into 3 equals square root of 6. Okay, so note this point. This is incorrect method. The correct method we have discussed solution of this example. Okay, now let's see some important identities. Okay, so let's start by recalling that the standard algebraic identities you already know also apply to complex numbers. So here, for any complex numbers z1 and z2, the first identity z1 plus z2 whole square equals z1 square plus 2 times z1 times z2 plus z2 square. And the second identity is z1 minus z2 whole square equals z1 square minus 2 times z1 times z2 plus z2 square. The third identity, z1 plus z2 times z1 minus z2 equals z1 square minus z2 square. Fourth identity is z1 plus z2 whole cube equals z1 cube plus 3 times z1 square times z2 plus 3 times z1 times z2 square plus z2 cube. And the fifth identity, z1 minus z2 whole cube equals z1 cube minus 3 times z1 square times z2 plus 3 times z1 times z2 square minus z2 cube. Now let's start by looking at a basic property of complex numbers. Here we have the expression z1 plus z2 whole square, where z1 and z2 are complex numbers. This is equals to z1 square plus 2 times z1 times z2 plus z2 square. Let's prove it. Okay, so we will prove it step by step. So we have z1 plus z2 whole square equals z1 plus z2 times z1 plus z2. Okay, this just means we are multiplying the sum by itself, which is the definition of squaring any number or expression. And now, since a plus b times c plus d equals a times c plus d plus b times c plus d, so using this, so we can write z1 plus z2 times z1 plus z2 equals z1 times z1 plus z2 plus z2 times z1 plus z2. Now let's distribute each term. So we obtain z1 square plus z1 times z2 plus z2 times z1 plus z2 square. Since multiplication of complex numbers is commutative, that is z1 times z2 is the same as z2 times z1. So we can combine those two terms and we can write it as z1 square plus z1 times z2 plus z1 times z2 plus z2 square. And finally we obtain it is equal to z1 square plus 2 times z1 times z2 plus z2 square. So therefore z1 plus z2 whole square equals z1 square plus 2 times z1 times z2 plus z2 square. Now let's look at another important algebraic identity, z1 minus z2 whole square equals z1 square minus 2 times z1 times z2 plus z2 square. So let's go through the proof of this identity step by step. So we have z1 minus z2 whole square, and this can be written as z1 minus z2 times z1 minus z2. So next, let's expand this product. So using here a minus b times c minus d equals a times c minus d minus b times c minus d. So using this we get z1 times z1 minus z2 minus z2 times z1 minus z2. Let's distribute each term and we obtain z1 square minus z1 times z2 minus z2 times z1 plus z2 square. And here multiplication of complex numbers is commutative. So z1 times z2 equals z2 times z1. So we can write it as z1 square minus z1 times z2 minus z1 times z2 plus z2 square. And finally we combine the like terms and we get z1 square minus 2 times z1 times z2 plus z2 square. Therefore z1 minus z2 whole square equals z1 square minus 2 times z1 times z2 plus z2 square. Now let's look at the third property, z1 plus z2 times z1 minus z2 equals z1 square minus z2 square. Let's move on to the proof of this property. So we have z1 plus z2 times z1 minus z2, and this is equals z1 times z1 minus z2 plus z2 times z1 minus z2. Since a plus b times c minus d equals a times c minus d plus b times c minus d. This is equal to z1 square minus z1 times z2 plus z2 times z1 minus z2 square. Since z1 times z2 equals z2 times z1, so this is equal to z1 square minus z1 times z2 plus z1 times z2 minus z2 square. And here you can see z1 times z2, negative z1 times z2 and positive z1 times z2 will be cancelled out, and finally we will obtain z1 plus z2 times z1 minus z2 equals z1 square minus z2 square. Now let's look at property 4. So let's begin the proof of this formula. So we will break down the expansion first. So we have z1 plus z2 whole cube. This is equals to z1 plus z2 times z1 plus z2 plus z1 plus z2 times z1 plus z2. Okay, and this is equal to z1 square plus z1 times z2 plus z2 times z1 plus z2 square times z1 plus z2. Let's expand this product and we multiply each term in the first bracket by each term in the second bracket. This gives us z1 cube plus z1 square times z2 plus z1 square times z2 plus z1 times z2 square plus z2 times z1 square plus z2 square times z1 plus z2 square times z1 plus z2 cube. Since z1 times z2 equals z2 times z1, so this is equal to z1 cube plus z1 square times z2 plus z1 square times z2 plus z1 times z2 square plus z1 square times z2 plus z1 times z2 square plus z1 times z2 square plus z2 cube. And now let's add up the like terms and we get z1 cube plus 3 times z1 square times z2 plus 3 times z1 times z2 cube square plus z2 cube. And now let's look at property 5, that is z1 minus z2 whole cube equals z1 cube minus 3 times z1 square times z2 plus 3 times z1 times z2 square minus z2 cube. Let's move on to the proof of this identity. So we have z1 minus z2 whole cube, and here we break down this as z1 minus z2 times z1 minus z2 times z1 minus z2. This is equals to z1 square minus z1 times z2 minus z2 times z1 plus z2 square times z1 minus z2. Now let's distribute z1 minus z2 across each term in the previous result, and we get z1 cube minus z1 square times z2 minus z1 square times z2 plus z1 times z2 square minus z2 times z1 square plus z2 square times z1 plus z2 square times z1 plus z2 cube. Since z1 times z2 equals z2 times z1, so this is equal to z1 cube minus z1 square times z2 minus z1 square times z2 plus z1 times z2 square minus z1 square times z2 plus z1 times z2 square plus z1 times z2 square plus z2 cube. Finally, after combining all the like terms, and we arrive the simplified result, that is z1 cube minus 3 times z1 square times z2 plus 3 times z1 times z2 square plus z2 cube. Okay, so this is our final conclusion. Z1 minus z2 whole cube equals z1 cube minus 3 times z1 square times z2 plus 3 times z1 times z2 square plus z2 cube. Now we will look at an example where we need to express some complex numbers expression in the standard form a plus iota times b. So in the first part, we have to express the following expression: minus 5 times iota times 1 divided by 8 times iota in the form a plus iota b. And the second part, we have to express the expression minus iota times 2 times iota times minus 1 divided by 8 times iota whole cube, okay, in the form of a plus iota times b. So first of all, try it yourself and then see solution. So let's look at the solution of this example. So for first part, let's multiply two terms: minus 5 times iota times 1 divided by 8 times iota. Okay, so this is equals to minus 5 times iota square divided by 8. Since iota square is minus 1, so this is equal to minus 5 times minus 1 divided by 8. And this is equal to 5 by 8. And it can be written as 5 by 8 plus iota times 0. This was the result in the standard form a plus iota times b, where a is here 5 by 8 and b is 0. Therefore, our final answer for part 1 is minus 5 times 1 divided by 8 times iota equals 5 by 8 times 5 by 8 plus iota times 0. Now, let's look at the second part of this example. So in second part, we have the expression minus iota times 2 iota times minus 1 divided by 8 times iota whole cube. So let's expand minus 1 by 8 times iota whole cube. Okay, so and simplify it. You'll get 2 times 1 divided by 8 times 8 times 8 times iota to the power 5. This is equal to 1 divided by 256 times iota to the power 4 times iota. Since iota to the power 4 is 1, so 1 divided by 256 times iota equals to 0 plus 1 divided by 256 times iota. Therefore, minus iota times 2 iota times 1 minus 1 divided by 8 times iota whole cube equals 0 plus 1 divided by 256 times iota. Now we will look at example 3. So in this example, we have to express 5 minus 3 iota whole cube in the form of a plus iota times b. So let's look at the solution of this example. So using the identity z1 minus z2 whole cube equals z1 cube minus 3 times z1 square times z2 plus 3 times z1 times z2 square minus z2 cube. Here z1 is 5 and z2 is 3 times iota. So we will substitute z1 equals 5 and z2 equals 3 times iota into the formula, and this will give us the answer. So we have 5 minus 2 iota whole cube equals 5 cube minus 3 times 5 square times 3 times iota plus 3 times 5 times 3 times iota whole square minus 3 times iota whole cube. Now let's simplify each term. So 5 cube is 125 and 3 times 5 square times 3 iota is 225 times iota. 3 times 5 times 3 iota whole square becomes 3 times 5 times 9 times iota square, which is 135 times iota square. Since iota square is minus 1, so this term is minus 135. Okay, and finally 3 times iota whole cube is 27 times iota cube, and since iota cube is minus iota, so this is minus 27. This is since iota cube is minus iota, so this is minus 27 iota, and here minus of minus 27 iota will become plus 27 iota. Now let's combine like terms. The real parts are 125 and one here 125 minus 135. Okay, so which add up to minus 10, and the imaginary parts are minus 225, then 27 plus 27, which sum to minus 198 iota. So the simplified result is minus 10 minus 198 times iota. Therefore, 5 minus 3 times iota whole cube equals to minus 10 minus 198 times iota. So I hope this example is clear to all of you. Now let's look at example 4. So here in this example we have to express minus 3 minus square root of 3 plus square root of minus 2 times 2 times square root of 3 minus iota in the form of a plus iota times b. So first of all, try it yourself and then see the solution. So let's look at solution of this example step by step. So first we will start by stating what we have. Okay, so the expression we have minus square root of 3 plus square root of minus 2 times 2 times square root of 3 minus iota. Now we use the property that the square root of a negative number that can be written as square root of minus a equals square root of a times iota. So square root of minus 2 equals square root of 2 times iota. Okay, so now our expression will look like minus square root of 3 plus square root of 2 times iota times 2 times root 3 minus iota. Let's expand the expression by multiplying each term. So this is equal to minus 6 plus root 3 times iota plus 2 times root 6 times iota minus root 2 times iota square. Now let's simplify further. So it will give us minus 6 plus 2 plus root 3 times 1 plus 2 times root 2 times iota, since iota square is minus 1. So ultimately we get the answer. Okay, so the expression minus square root of 3 plus square root of minus 2 times 2 times root 3 minus iota can be expressed in the form of a plus iota times b as minus 6 plus root 2 plus root 3 times 1 plus 2 times root 2 times iota. Okay, and this is our final answer. So that's all for today's lecture, and thank you for your attention. I hope this lesson was helpful to all of you.